emphasizing on the RAD750 and PowerPC architectures. Thank you, Ranjit, for that short introduction. The quick purpose of the webinar was to really present how a virtual prototyping on the computer can enable you to get very detailed and accurate information about task scheduling and hardware architecture exploration in terms of system sizing and bottleneck analysis. Allows you to be able to predict in advance how your system is going to behave once you actually deploy it in the real spacecraft. In addition to that, what it also gives you is an insight into how the customer experience is going to be in terms of being able to understand what solution you're proposing. A quick introduction to Merlin Design. We're a provider of model-based system architecture exploration software. The technology is called Visual Sim, and it's being widely used for everything from software scheduling analysis to system sizing to energy or power management, and of course reliability analysis. I'll be covering most of those during the presentation, as you will see. Merlin Design as a company provides the software Visual Sim technology, but also provides the services to enable and provide a complete customized platform for your projects. We're based in Silicon Valley, and we have experts that have considerable years of experience in system modeling and architecture, right from anything from Amdahl mainframes to processors to spacecrafts to avionics to automotive systems. A quick introduction to the product Visual Sim. Visual Sim is used in a variety of areas. The main focus is hardware, software, RTOSes, interfaces, the mission level analysis as well. And it's completely graphical, where you create these hierarchical building blocks that allow you to describe your subcomponents or your subsystems. The technology, is everybody still able to hear me, or are you still having problems?
I'm hearing this fine.
Okay. Thank you very much. It looks like a few people are still having some problems. Okay, good. Thanks. Okay. So the technology Visual Sim has a large library of cycle accurate and stochastic components that have timing, power, and functionality embedded into the system. So what this allows you to do is very quickly assemble up systems right from your traffic to the system definition to the analysis using just these building blocks. Now, one of the key questions is, why use virtual prototyping in Visual Sim when I can just acquire a board and be able to do this everything within on this physical platform itself? A couple of reasons that it comes to mind right away. The first one is just the cost of acquisition of these boards. The second one is the limited capacity of boards that you can actually have in your lab. But the more technology effect is that you want to try a large number of variations. Setting up a large number of variations on a physical board is a fairly long task. It can take weeks, sometimes even months. So it sometimes becomes unviable to be able to configure these boards to handle all these different variations. The second thing is, a lot of times the software is not available, and being able to have a board without the real software does not make a whole lot of sense. The last one is, the board is really for being able to visualize what happens end to end. If you want to have insights into what's happening inside the RAD750 or inside pieces of the board, it's really not set up to provide you those kind of task activities or your buffer activities, or how much MIPS you're getting out of the processor, things like that. Especially in technologies like the RAD750, where you only have about 200 megahertz and you have considerable amount of software that needs to be loaded, you need to be able to get maximum capacity utilization. So one of the things that Visual Sim provides is a concept of end-to-end system analysis. What that means is, right here, what you can see is, not only do you have the battery and the photovoltaic cells, but you also have all the elements that consume the load, right from your RF transmitter receivers, sensors, your microcontrollers, any accelerator components. These form your actual physical systems. In addition to that, what you also get is the ability to define your workload and use cases. Now, one of the things about the use cases, a lot of it can be described using text and tables, which are in Excel or in a CSV format. Now, I'm going to move over to the Visual Sim software so you can actually see what it looks like. So this one here is the Visual Sim modeling environment. As you can see, there's the libraries on the left-hand side, and as you can click on some of these components, you can see that there are a number of components that are already predefined over here. Now, using these components is what you use to build these models up, and then of course you can set up things like your table of these different use cases. You can also use it to define your power information for each of the components. So you have ability of those. Plus, you can set up attributes that might vary from simulation to simulation. Now, with this model, what I can do is I can actually click on the Go button over here, and I can go ahead and run a simulation. What will happen is that you will see a variety of reports that are generated. Now, the reports that are actually generated depend on the type of analysis you want to perform. So in this case, our interest is in getting an overall view of your system. So we're looking at both the energy consumption and the time that it takes to complete these different tasks in the use cases. So we have, for example, 4 tasks that are listed over here. So one of the things you can see over here is the power consumption, so the battery usage. And you can see we actually let the battery get consumed at about 50% of consumption, and then we start charging it up again. So we don't just keep on continuously charging the battery. Purpose for doing that is to analyze what is the life expectancy of the battery. You know, if you just consume it, well, I mean, once you recharge it only after you completely drain it, what is the battery life? Does that extend the battery life? So it allows you to analyze that. What do you get out of this? A couple of different things. One is it tells you how much of battery sizing you need, you know, how much of the charge circuitry you need. It also tells you what is the available unused power in the battery. This is important because what it does is gives you an idea on how much more you can load into the system. You know, can you add like maybe another RAD750 board? Can you add maybe a few more hardware devices? This one here gives you a visibility into what is your time that it takes to complete these different tasks based on your particular architecture. One of the key things is you're going to have a lot of questions while I'm going through the presentation. As we have muted all of you, it will be good if you go ahead and type your questions into the chat window on the control panel on the right-hand side. This ensures that some of our technologists that are online can immediately answer your questions. Now, what does Visual Sim virtual prototyping really provide you? First and foremost, it gives you a solution where you can actually visualize for yourself and also demonstrate to, say, the program office or your customers or your suppliers what it is that you're building. Is it going to work? Is it viable? The other part of it is when you're putting in a new proposal, you don't want to be able to try to acquire a board, try out an experiment, see is it going to work, but rather you want to be able to quickly size and verify the feasibility of your proposal before you actually deploy it. The other one is scalability. How is this solution going to scale when I load some additional software or load some additional programs? So while it is in space, I might decide that I might want to add a little more imagery, or I might decide I want to add the capability to maybe do some mapping of a remote planet. So when I load up the software, how is the system going to perform? Is it going to be able to handle that extra load? One of the key things in systems engineering is that all the specification is defined using SysML, and all the algorithm development is done in MATLAB. There is a kind of a gap between the two, meaning once the SysML tasks and state machines are defined, there is really no contribution to determine what is the implementation of these SysML tasks. Do I put them on a Zinc 7000? Do I put them on a Vertex 4? Can I, is the RAD750 sufficient? The other one is when you're designing the algorithms, you have to know how you're going to implement it, because that's going to determine how many say quantized values I can use in my MATLAB algorithm. That is where the Visual Sim prototype allows you to get a complete visibility into this is exactly how the implementation is going to be. This is exactly what the hardware platform is going to be doing. So this is where the Visual Sim virtual prototyping is going to assist you. One of the other aspects of systems engineering is about sharing and communicating. So you have the system architects that are developing these models, doing analysis, determining what the power and performance is, looking at reliability, fault tolerance, things like that. But then the same models can be shared with your customers and suppliers by providing them access through a web browser. So what it means is, for example, a firmware or software group can look at this, incorporate their algorithms in, and see what the behavior or performance is going to be. But in addition to that, what you can also do is be able to provide maybe a training facility for your upcoming engineers, or provide a kind of a sneak peek for your customers to see how you're progressing in your development. So for example, right over here I've got one of these links that's on our website. So I'm going to move over to the Visual Sim, to our Mirabilis Design website, where you can actually see a documentation that's already in progress. So this is something where we've got this rapid I/O based system that has a large number of Power PCs and RAD750 type architectures with Xeons and multiple interfaces and boards, including a PCI Express backplane. This is the model, which right now, as you can see, is static. But then what has also been attached to the same model, I'm going to bring that up in a second, is right here. You can see this is coming from our mirabilisdesign.com website, is the actual simulation model, which is now available right from within your web browser. So you can actually run simulations right from within the browser, and where you can actually view some of the results, like right here. You can see what was the latency of all the activities on your MPC 8000 series, or you can see the amount of MIPS that is there. You can see that the range is about 50 MIPS is what you're getting on that particular architecture. What you can also do is get visibility into my read throughputs, what's my latency for my reads and writes. I can also get visibility into what is the effective throughput on another part of the system. Also be able to visualize, for example, what's the amount of MIPS I'm getting out of the Xeon processor. You can do all of this from right over the web browser into a private cloud that you have within your organization that you're giving people visibility into. So now your virtual prototyping is not just helping for your internal systems engineering, but also for you to be able to communicate with your customers. Questions have been coming by, and I know that some of the people are answering some of these questions as they're coming by. Feel free to keep entering these questions. Now, going directly into the RAD750, one of the key things is that we in Mirabilis Design do not just provide a hardware platform. We provide a complete virtual prototyping solution around the RAD750. What that means is that, yes, you do get your hardware platform, but in addition to that, you get traffic generators, the visual GUI to configure your system. the operating system or scheduler associated with time-space partitioning like an RAD750, but you also get other kinds of schedulers like first come, first serve, round robin, weighted round robin, things like that. You also have the ability to define what your software tasks are doing. You don't really need your software, you don't really need the C code, but rather the ability that we provide you is with completely through spreadsheets be able to define what your tasks and activities are. So what does that really mean? We will be providing the slides and a link to the video at the end of this presentation, so you can study it at a later time. Now, with regards to the different pieces, let's focus on the input side. So the input side consists of the traffic generators, which can be, say, data coming in on an Ethernet interface or some sensors or imaging equipment. The key attributes there are rate, how fast or how quickly the data is coming in, what's the size of the data, and of course what is the priority. The other part is configuring the real hardware, everything from the clock rate to what your L2 cache size needs to be, to what your external buses are, to what the software scheduler slot sizes are. The third part is the actual scheduler itself. So this is the input piece of your RAD750 solution. Now, this is the top view of the RAD750. As you can see, there is the hardware board. Those are the components, those are the elements that you're using to define your architecture, which is your hardware. There's your traffic generator. This is your definition of the tasks. And this one here is the actual scheduler. In this case, we're using a time-space partitioning around RAD653. And these are defining your software tasks. Now, when I zoom into this particular block over here, what you're going to be able to see is more details about the hardware architecture. But before we do that, I'm going to move to talk about this actual software tasks. The tasks are either defined as periodic messages or events, and each of them has a priority with a deadline associated with it. The task itself is defined as a list with association with slots. Each task has read, write, request from resources, and execute. In addition to the task itself, you have events that can be periodic or interrupt driven, and there can be messages that can be triggered by the task, or they can be independently, periodically set up, which can then trigger other tasks. So these are how the tasks themselves are defined. To look at the view of how these tasks are, here's one of the tables that we have in the system. You can see these are the RAD653 partitions, the names of tasks, what's their frequency of occurrence, the read and write data sizes, what are the different variables, what is the priority of the task, and how much time is it going to take to execute on the RAD750. Now, using this, so we have the input, now we have the definition of your software and tasks. Now we look at the hardware solution. The hardware platform itself provides you both the DRAM 2 and 3. It also gives you the cache, the DMA peripherals, and also the PowerPC that work around the RAD750. In addition to that, associated with each task, we have a profile set up that allows you to generate an instruction sequence associated with that software. So you don't actually need to compile and load the software, get the operating system running, getting GCC, none of those are required. Rather, the tool takes care of all of that. All you need is tell us certain descriptions about each of the tasks, and a software profile is generated for that particular task. So this is the internal view of the hardware platform. You can see that's your processor with the cache. That's the bus with its bus multiplier right over here. You have the external DRAM. You have a bridge to connect it with any of the other peripherals you want. It's got the instruction set, and it's got all the different attributes associated with the L1, L2, and with the speed of the processor. Now I'm going to move over to the RAD750 itself, model right here on the platform. That's the RAD750 platform that we provide you. And as you can see right over here, this one is the MPC 750. And this one here is the PowerPC architecture that's been defined. It's got the IND caches, the L1, it's got the pipeline, it's got all the integer units. It also has the bus, as we talked about, the external DRAM. So it has the complete hardware platform, and then it's got all the associations with the rest of the system. So for example, here's your task list that we saw earlier with a variety of tasks that have been set up for each of the partitions. We also have the task generator right over here along with the task scheduler. So when I go ahead and click on Go here, you're going to have a variety of statistics that are being generated. Right now, the one that we are most interested in is going to be the statistics associated with the PowerPC platform and the latency associated with the completion of those different tasks. So what we're really interested in is, are those tasks completing within a deadline? Now, moving on to looking at some of the analysis. So while the simulation is running, we're running the simulation for about 5 seconds of wall clock time. So it takes about maybe a minute to a minute and a half to complete that simulation run. So while that's running, we're going to continue to talk about the analysis. The main goal here of the analysis using the RAD750 is twofold. One is, can the tasks be completed within the deadline based on the scheduler that we're using? The second one is to determine, is there any possibility of system failures? And the system failure is being caused by what? Is it a lack of system capacity? Is it a buffering problem? Or is it priority of the events? To be able to get a full view of that, these are the types of statistics that we generate: the throughput, the hardware statistics, the battery and power profile. So now looking at the model itself, you can start seeing right over here the latency of these different tasks. You can see that we started off with some of these tasks that are right here at about 4 times e to the -4, so it's about 400 microseconds. But which these 3 tasks are really not meeting the deadline. Now you notice most of the tasks are able to meet the deadline. They're right over here. Then you start wondering, why are certain tasks being able to meet the deadline and certain tasks not able to meet the deadline? For example, over here, this task actually overshoots and is not able to meet the deadline. So you're trying to understand why that is the case. One of the things we got to do is not just look at, okay, this task did not meet the deadline, but rather, what caused this task to not meet the deadline? There are 2 parts to it. One is to analyze what are the tasks that happened immediately prior to it. So you notice there's a long tail for the previous task that completed, and then this was arrived only at this time to actually start executing. So what this tells me is that this task was actually buffered or waiting for an extended period of time before it can actually start, before it could start scheduling. Oops, sorry. This software can actually run on Windows, Linux, and on Macs. Our development platform is on the Mac, but then we do have a lot of customers on Windows and Linux as well. Now, when I look at the hardware statistics of this particular system, one of the things that's going to come up is that I try to look at first is looking at what are the stall time, which is what percentage of time the processor is not active. It's waiting for something. And notice it's about almost 13.5% right over here. The other thing you'll notice is that the bus activity right over here, you see that we have considerable amount. We've got almost 185 megabytes or mega IOPS. The other aspect here is the buffering. Notice over here, the input buffer occupancy is actually 5 words are being buffered at any time. What this immediately tells me is that there's a lot of backup in the access to the DRAM. So it means that a lot of data requests are going out to the DRAM and coming back, and that's causing a lot of the system bottleneck. it ran a few more statistics out. I'm going to skip some of those, just focus on one of these. The other aspect that I want to look at is my hit ratio. Notice I only have an 84% hit ratio on the iCache. So this tells me that, one is that the internal cache is insufficient. The application software is actually being loaded on and off, prefetching, and misses are going back and forth between the iCache and the external DRAM. So this is another reason for why you're starting to see this huge amount of backup, of buffering that's happening in the system, plus an extensive stall time. This is something that only a virtual prototype on the computer can give you visibility into. It'll be very hard to get this kind of visibility directly out of a hardware platform. And this is where Visual Sim really plays a role, where it provides you the ability and the visibility into the details of the system. So when you receive the RAD750 platform, as I mentioned, you don't just get the hardware. You get your task generators, your schedulers, your setups, your task or your software definition. You get a complete platform that you can use to very quickly set up and be able to do the analysis. Now, one of the key things that can also happen is, if I go back into the RAD750 platform here, not only can I keep this RAD750 here, but I could possibly even extend it to adding other vendor products. We've got over 100 processor family, so you can actually add other processors. So for example, you can offload some of these to say like a Xilinx Vertex 4, Vertex 5, or a Zinc 7000 family. You can also look at other processors for certain tasks that are not that radiation impacted, and you could add those and see how the system behaves. So this system is also fully scalable to be able to handle additional additional patterns or additional hardware elements into the particular system. Now, one of the views that we have put in here that gives you a better visibility into the system is showing you what are the activities or writes and what are the actions that are being active in the system, plus certain amount of refreshing or setup or context switching time around these systems as well. And associated with that, we have it lined up against the power consumption. Now, one of the things you're going to notice is that there's a lot of spikes over here in terms of power consumption, while if you look at the average is typically what you get in terms of your power data. But what you have here is, in addition to the average, you also get visibility into the peak power. This being important because this converts to what your thermal consumption is of your system. It gives you a view into what your cooling requirements are going to be. It gives you all of that right up front while you're doing these analysis. Additional view that we looked at earlier was the MIPS. So you can see that we are between about, it's a 10 to the power 2, so you're between about 137 to about 146 MIPS. So you're actually fairly efficient because you're about 70 to 75% of the total capacity of your PowerPC on your RAD750. So the task setup that we have and the task scheduling that we have done is fairly efficient because we see that we're using almost 75% of the capacity, which means we're kind of at the upper limit of where you can go with this architecture. Now, RAD750 is there, but as I talked about, you can actually go beyond just including the RAD750 in your system. One of the key things is that we have the largest portfolio of hardware libraries, and I'll be talking about that in a second. We also have over 25 schedulers that we've implemented internally. So those are also available for you to experiment with additional scheduling options on implementing your software tasks onto the platform itself. Set over 100 processor models. We've got over 200 projects that are being used around task scheduling and hardware sizing with Visual Sim. One of the key things is we have probably the largest model capacity that you can do with any system model. To give you an idea of what we have, this is our system level IP. As you can see, it's a fairly large collection, and it actually grows almost on a daily basis. We are constantly churning out newer and newer library components. So, to find out what the latest is, always visit our website or contact some of our application engineers for more details. Now, large capacity. We saw one RAD750. Now here what you're looking at is we've got 15 of these RAD750 boards with traffic generators connected through PCI Express backplane to a variety of external DRAMs that are communicating to them. So what you can do is you can actually combine a large number of these platforms into a single model to see how the overall behavior of this platform is going to be. So what it sees is that you can actually see how my entire spacecraft or my entire launch vehicle or entire flight control system is going to behave. It's not just restricted to how does this one board behave. So I don't actually have to buy 15 boards. I can just buy one, I can just buy one environment and just instantiate multiple of these boards here. Now, in terms of the exploration expansion, of course you can use the ARM and Intel platform. I showed you a Xeon processor, but we also have a whole variety of ARM-based platforms. You can also bring in, as I said, the Vertex 4s and 5s. All of these, so there's a base product, and then there are libraries built up on the base product. So you as a user can buy just the base product, which gives you all your simulation platform, your analysis tools, your basic library, scripting language, but it also provides you the certain hardware library which you pay an extra charge for. Now we do support Altera library blocks, but those have been given on a case-by-case basis to a certain customers, but we do provide Altera as well. Also, we have a number of high-speed interfaces, SpaceWire, Rapid I/O, Ethernet, PCI Express. One of the key things we have in Visual Sim is the ability to run multi-core and multi-processor platform. So as your system starts scaling to large number of cores, maybe even tiered things like like GPUs, we have environments for you to be able to construct those kind of systems as well, to be able to incorporate into your overall exploration. Another aspect which may not be directly on the RAD750 but works in the context of your system is the energy harvester library. What that is allows you to visualize my different energy harvester models, and it has key attributes for each of them. So for example, the PV cells are going to behave entirely different from, let's say, a small nuclear reactor to a motor that generates the power. But it allows you to create all of those and incorporate that into the bigger system and be able to link that with the battery and also be able to visualize in terms of the, I'm just going to move into a model that shows you exactly how that's done. So right over here, as you can see, there's the PV cells, that's the battery size and what the update is, and there is the battery itself. So you can actually, So you can also, in this case, what you can do is with regards to the battery, you can actually see for different orbits, what is the subsystem activities and what is the instantaneous and average power. So one of the things that a lot of times we focus on is you tend to focus on the average, which is the red bar over here. And what we do is we tend to leave out the instantaneous power. And those are those peaks that you're seeing over here. They may not be around for a very long time just for these small states. But then what they are, again, as I mentioned, are very critical in terms of determining your cooling cost, your insulators, and things like that. And also, what your temperature range is going to be ending up at. So, again, the energy harvester is actually a complete system, provides you the ability to visualize how your power consumption, how your power generation is with regards to the consumption of your overall system. Now, one of the aspects in Visual Sim and the power related is that we don't work on average values, we don't work on an analytical model. Rather, we work on a very dynamic power analysis. What does that mean? If you look at each one of these devices right here on this particular board, you see that we have for different states a power value. Now, when you actually do power analysis using a spreadsheet, you tend to take an average of these values, you add it up for different use cases, and you come up with an average number, which if you notice in Visual Sim, it generates those in a slow-moving case. Now, what happens if you have concurrent activities? What happens if you have events and triggers? Your power profile changes dramatically. In this case, you're going from about 1.1 to about 1.6. So you're looking at almost a 40 to 50% jump in the power, which can be actually analyzed with an analytical system. This is where the dynamic nature of the power analysis comes into play or makes a difference. Now, the other aspect is the power management, and we do provide you a power management platform in the form of a state machine that allows you to define all the different power states and define what are the conditions or transitions to go from one state to another. So it provides you a completely graphical way for you to define your power manager. Now, if you look at Visual Sim and the RAD750, how does it actually help your project? The real way it's going to help your project is that you're able to very quickly create these models, do analysis and refinements well in advance of your implementation, which means you already know how you're going to implement it before you start writing your MATLAB code, before you start doing any Verilog or schematics, any of those. You're actually being able to do your analysis right up front. And then you go off your implementation. So what happens is when you're in your implementation, you immediately know what is available and how it's going to work before you actually even start deploying anything or even try to do any testing. And we've actually done surveys of our customers, and we've seen about 20 to 40% savings in terms of the time schedule, in terms of the project schedule, and in terms of the reduction in the number of errors that you have during the implementation. With this, I would like to wrap up my presentation on the task scheduling and hardware sizing for RAD750 platform. Hopefully you got understanding of how the RAD750 platform that we have works. And you're able to understand how the tool is set up for you to do your analysis, and how we provide you a complete platform that you just have to vary values to be able to make your analysis. Our application engineers are standing by to answer any of your questions, so feel free to enter your questions into the chat window.